we're still talking about Preflow-Push. This is one of the, I think it's a great algorithm. At any rate, I'm not going to write up everything that we wrote last time, all the details of the algorithm itself, just to remind you that there's a push procedure which takes in your current preflow, takes in the labeling, and you're pushing from V to W. And there are two things that I will remind you of. First of all, that edge VW, that of course has to be in the residual graph at that moment. So we don't know if this is a forward edge or a backward edge, but it's in the residual graph. You only get to push on edges that are in the residual graph. And we also need that you're always pushing from a higher node, a node with H label bigger than where it's pushed to. Okay? So those are two requirements. And let me also remind you that we relabel, that is, again, you have a preflow, you have an H, and you have a single node V, and if you can't push from V, there's no push possible there, then you set H of V equals H of V plus 1. Okay? So you just increase its height, and then it makes it more possible, more likely that you're able to do that. And then we also had this thing called compatibility. So there was a compatibility between a preflow and a labeling. And that was that for, if you had an edge, VW, in the residual graph, then you had to have H of V was less than or equal to H of W plus 1. Okay? The edges in the residual graph could not be too steep if you think of these as physical heights. All right? Now, in the algorithm, where we had stopped last time, I was giving you a proof that the algorithm always maintains compatibility. It starts with compatibility. How does the algorithm start? It starts at the source, S, and it saturates all of the edges out of S. Okay, so this is the start. It sets F of E equals CE for all E, all edges E out of S. And otherwise, it sets it to 0. And it also sets H of S equal to N, H of T equals 0, and H of V equals 0 for V not equal to S or T. Well, V not equal to S. Yeah?
Does it say right there, right next to the F comma H?
This one?
Below. Something, something, F comma H, V to W. Oh, what's that?
Compatible. This is the definition of compatibility. I'm going through this very fast because we've done it in case of compatibility. Well, at least maybe even 2 lectures ago, it was defined. Okay, and so all of this is review. So let's do it very, very quickly. All right, so the algorithm starts by setting up this preflow, and we saw last time that this preflow and this labeling H are compatible. And then where we ended last time, I was trying to convince you that in the Preflow-Push algorithm, I said, well, by the way, what is the Preflow-Push algorithm itself? It has these 2 procedures. Well, you just look, I'm not going to write this down, the algorithm just finds some node that has excess. And it tries to get rid of that excess through pushing. And if it can't get rid of the excess through pushing, then it tries to relabel, or does relabel, and just keeps going. And it stops when there's no excess. Okay, so there's something to prove there, because maybe it gets stuck somewhere because it can't push, and yet well, I mean, it's really nothing to prove. If you have excess at some node and you can't push, then you increase the label. And if you still can't push, you increase it again, and so on. Ultimately, it's going to, the height of H is, the height of V is going to get high enough that because there's excess at V, there must be some edge in the residual graph from V somewhere else where it actually had received that edge, that flow originally, that excess originally. And ultimately then V is going to get raised up and you'll be able to push out of V. Okay. So the algorithm only ends when there really is no excess at any node, and we've argued previously that that's when you have a flow. We've even argued that at that point it must be a maximum flow because there's no S to T path at that point. Okay, but the key, the linchpin of this entire argument is that throughout the algorithm, the preflow and H remain compatible. Okay, so that's where we stopped last time, and so let me just put that up again. F and H remain compatible throughout the algorithm. And we just got a little bollocksed up with the notation last time. It's really a very simple matter. So this time I'll actually look at my notes so I don't get confused. Okay, so what happens during the algorithm? We either have a push or we have a relabel. I mean, the only things that can change either F or H are a push. Well, it can change, that'll change F or that'll change the residual graph. Only thing that changes H are the relabelings. So where were we last time? If you have a push, let's look at what happens in pushes. You push from V to W, okay? This edge, let's say this edge had been it's a forward edge and the push saturates it. It puts a flow now equal to its capacity. Then this edge actually goes away from the next residual graph, okay? If it had been a backward edge, and again, this is in the path, this is a backward edge, that means then the flow from W to V decreases, and it might actually decrease to 0, that's possible, in which case this edge goes away from the residual graph. The edges disappearing from the residual graph don't lead to violations here. So I should have said we're doing an induction, essentially. Imagine that the F and H are compatible up to some point in the algorithm, and they started out compatible. Then we do something in the algorithm. What changes? The residual graph might change in that some edge that we just pushed on disappears from the residual graph. So that's certainly not going to affect, where is the definition of compatibility? Yeah. If edges disappear from the residual graph, they certainly can't violate. That won't cause a violation of compatibility. But it could happen that an edge actually enters. So this edge, WV, enters GF due to a VW push. What kind of a push is that, by the way? I mean, what kind of an edge, if that happens, what kind of edge was VW? Do we know? Well, certainly if it was if that was a forward flow, I mean, this could come in as a back edge if this had been a forward flow initially of 0. The flow had been there of 0. If this is a back edge, I guess this could be a back edge where the flow is already up to its maximum capacity. So I guess we don't know, but it doesn't really matter. Okay, there could be a V to W push, right? Which causes W to V to enter into the residual graph. And so now we have a possibility of violating compatibility because there's some new edge. So we want to make sure we have compatibility there. But in order to have pushed from V to W, we needed h of V greater than h of W, right? When we push from V to W. That's a requirement for pushing, okay? H of V has got to be greater than h of W. So we knew that at that moment. And so now we're looking at compatibility. What's compatibility say? Compatibility says that, this is why these V's and W's play different roles, and that's why I relabeled them last time, but I got myself confused. So we'll just do it. We need now that if you have an edge from one node to another node, okay, up here it was described as V and W, but they're just variables, right? If you have an edge from a node to another node in the residual graph, you need that the h of the first one is less than or equal to the h of the second one, okay? So what do we need over here for compatibility? After the flow, after the push, what do we want? We want this edge to be compatible, right? The edge that goes from W to V. So we need what condition? Yeah, h of W is less than or equal to h of V plus 1, okay? But we already have h of W is strictly less than h of V. So you certainly have satisfied this, okay? Now, where this gets tricky is because the role of V and W here, I mean, V and W here was just, if you just think of these as just names to define this condition. Okay? But when this condition is applied over here, which was the head and which was the tail of the edge, the V and W changed. They changed roles, okay? I think that's how we got ourselves confused last time. We didn't pay attention to that. All right. So certainly when an edge comes into the residual graph, we have no trouble with the condition of compatibility. That is that the label on the head of an edge, actually I never know what's head and tail on an edge, but anyway, the label on the node which is at the beginning of an edge has to be less than or equal to the label on the edge at the end of the node at the end of the edge plus 1. And we have that. Yeah. Got a question?
Are you sure the HW and HV shouldn't be switched? Because I thought that it was if V flows to W, then W should be at least one lower than V, if not higher.
Okay, we'll go through this again. So your question is, am I sure that I did this right? The answer is no, I'm not sure. But I think it's right. Okay, so we have a push from V to W. In order to do a push, of course, we have to have h of V greater than h of W. That's a condition for a push from V to W. Okay? Mm-hmm. Once that happens, it may be that the edge W to V comes into the next residual graph. Mm-hmm. And we're trying to verify that, that we have compatibility between the preflow F and the labels H. Okay, well, what that requires is looking at the residual graph at that moment. This edge just came into the residual graph. And what you need for an edge in the residual graph for compatibility is that the label of this node be less than or equal to the label of this node plus 1.
Oh, I'm sorry. You're completely right. You're talking about the WV edge, not the VW edge, and that's why.
Yeah, I know. I'm pointing out. I think last time what I did was I tried changing the labels of these things, so we weren't using V and W during the argument, but only during the definition. And then we used a P and Q during the argument, but then we got confused. So this time I'm doing it this way. Okay. What else can happen during the algorithm? You have a push, you could also have a relabel. Okay? So we want to make sure that we have compatibility after a relabel. A relabel of a node V. Okay, so here we are at V, and it has excess. Okay? So in that excess, we're trying to get rid of the excess. But you only relabel when you can't. So what happened? Why couldn't we get rid of the excess? Why couldn't we push out of V to some other node W? Well, I argued earlier that there's going to be some edge out of V in the residual graph. I guess I should have proven this by induction, that if a node has excess, then you will have an edge out of V. If a node V has excess, you'll have a node V in the residual graph, if only because if you look at the last edge that pushed some flow into V, that the residual edge for that push will be in the graph. And in fact, I guess I don't know where this comes in the argument, but we could also prove that if a node has excess, then in the residual graph, there's a path from that node all the way back to the source. Just by making the same kind of argument. You say, okay, V has excess. What was the last push of flow into V? Came from somewhere, so that reversed edge is going to be, a real flow, not backflow, backward. If it has excess, there has to be some moment in time when something pushed some flow to V. And therefore, the backward residual edge is going to be there. Okay? And then so on. You just keep arguing backwards, and you'll find a path. You prove by induction that there will be a path back to S. Well, anyway, so when we're looking at V, trying to get rid of its excess, and we can't, it's not because there's no edge out of V. There is an edge out of V. So what is it because? It's because for all of those edges, we have this relationship. We don't have this relationship anywhere. We have H of V is not greater than H of W. All right, so we have a relabel, and if we look at all the edges, this is in the residual graph. So we don't have H of V greater than H of W. Because if we did, then we'd be able to do that push. Okay, so what does that mean? What do you have if you don't have H of V less than H of W? Sorry. If you don't have H of V greater than H of W, okay, so H of V is less than or equal to H of W, right? That's the opposite. Well, and what do we want for, and now we're relabeling, relabeling V, right? How much do we relabel V? By 1. So after relabel of V, we have H of V less than or equal to H of W plus 1. And that's what we wanted for this edge. So for the edge that goes out of V when V is relabeled, that's what we needed. Okay? Anything else that we have to pay attention to? Well, I guess there are edges, because we're relabeling V, there could be an edge that comes into V. All right? What shall I label this node? Just to confuse everybody. Let's call it P. All right? All right. What do you need for, what did you have before you relabeled H? Remember, we have a compatible labeling. This is proof by induction. So before we relabel V, we have compatibility. So H of P is less than or equal to H of V plus 1. But when we relabel H, it's going up. right? When we label h of v, it's going up. So again, this relation is maintained, and therefore we have compatibility. Okay, so we always have compatibility. And now I will state something as a lemma or a claim. Maybe I proved this the last lecture or the lecture even before that, but anyway, if f and h are compatible, no, I don't get it, and EF is greater than 0, EF V, so the excess, V has some excess, then there is a path from V to S in GF. And induction number of operations. So initially, you know, here, of course, when we started out, we saturate all those edges out of S. And what you get in GF are that. So there's a path from every node that has excess. These are the nodes that have excess. And there's a path from every node that has excess back to S. And just apply do an inductive proof, again, looking at what happens in the algorithm. You either have a push or you have a change. Well, a relabeling certainly isn't going to change the graph. A push might, but at any rate, it's a very simple thing to establish. Okay. We may need that, but at the moment I don't see why. Okay, 9, page 9, page 7, 10, 11. What's after 11? 12. Okay. Yeah, okay, so that's, that actually is what comes up next in my notes. So we need that. All right, so now we can actually start proving something about the algorithm. Is that clear to everybody what the algorithm is and what we've established so far? We've got compatibility, we've got this thing, and so I'm going to start proving some little claims which will eventually show us that this algorithm actually does terminate and that the algorithm, well, actually with this thing, termination should be clear, okay? Because again, if you're at a node that has excess, there's definitely some edge out of it, according to this. And if you can't push, it's because the label is too low, but this is just going to relabel. There's no bound on how many, there's no bound in the algorithm on how many times you can relabel. So you relabel enough until finally you can push along this edge. And okay, I guess termination isn't quite yet clear. I mean, not clear why we're making progress. But anyway, we're not going to get stuck somewhere where you can't ever do another operation. Yeah?
I'm actually still a little confused about this relabeling process. If we're trying to push from V to W, then why, it looks like we've just increased the label of W and not the label of V. Because if you look at your equation below, we have h of v after the relabel is h of v is less than or equal to h of w plus 1. But weren't we trying to make h of v larger so that we could push from v to w?
Well, yeah, that's true. We want to do that eventually, but that's not part of this. This is trying to prove that the algorithm always maintains compatibility. So when the algorithm does something, it either does a push or it does a relabel. Okay, it's only the pushes that can change the residual graph. And it's the residual graph that's at the heart of the definition of compatibility. So we looked at what happened when you can change the residual graph. That was over here. The relabels don't change the residual graph, but we just wanted to say that they didn't violate compatibility either, because if you had compatibility just before the relabel, and you relabel it V, then it had to be because you weren't able to push out of V. So you had to have this relation for any edge that was in the residual graph. So you had this relation. And then when you did the relabel on V, it goes up by 1. So you have this relation, which is what you need for edges out of V to still be compatible.
But then H of P is still below H of V even.
Well, then we had to look at those edges that actually go into V. So this was for edges that go out of V. We were in good shape. What about the edge that goes into V? Okay. Well, that's going from P to V, so you had to have that relation for compatibility. And then when you increase H of V, you still have this relation. Okay. H of P doesn't change, but H of V goes up by 1. So
what you've just proven is that relabeling V doesn't mean that you have to push from a different node P into V. If you relabeled V one higher, then H of P is still below H of V.
Yeah.
And therefore you won't have to go reiterate and push more from.
Well, having to push is a different issue. We're just trying to prove compatibility. That's the only claim. This board here was just to establish the compatibility that the preflow, that is F and H, always remain compatible. What we actually do with these, we're not finished with the full analysis of the algorithm by any means. Okay, we've established compatibility, and we've established that fact over there. All right, now what do I want to erase? This is probably the most important thing to keep. This is the start. Okay. H of V less than or equal to 2n minus 1, all V. Okay. So yes, this algorithm, okay, so I'm ultimately trying to prove this algorithm actually stops. And it stops, the termination condition is that there's no excess at any node. And again, we've seen that that means that there's a flow, and we've also seen that because there's never an S to T path in the residual graph as this algorithm goes along. Actually, how do we know that? I remember 2 lectures ago what I proved is that if, there was a conditional, if the preflow F and the labeling H are compatible, then there's no S to T path in the residual graph. Okay? But we couldn't say that, therefore, the algorithm ends with that condition at that point, 2 lectures ago. Now we can, because we've actually proven that the algorithm always maintains compatibility. So now that we know that the algorithm always maintains compatibility between F and H, now we can say for sure that if the algorithm terminates, then it terminates with a max flow. So now we're looking at, does the algorithm actually terminate? Or maybe it just spins its wheels forever. Maybe it tries to push and it tries to relabel, and it's sending flow back and forth, and who knows it's doing anything really useful. Well, here's a first step. This is saying the labels don't get arbitrarily large. Okay, and notice when you relabel, you never decrease. There's no way labels ever decrease. They only increase. So if this is true, we've done a good thing. We've bounded how many times the algorithm can relabel. Okay. All right. So why is this thing true? Well, let's look at that back path that I just argued is always there. So from V, let's say okay, before I actually get there. When V is relabeled, we know it has excess. EF V is greater than 0. Okay, because that's by the algorithm, you can only relabel if you actually have excess. You can't push from V, and pushing is only when you have excess. Okay, so it has excess. That means that there's this path. There's a path from V to S in the residual graph. What's H of S? It's N. Okay? So what do we know about the H label of this node? It's, yeah, so I have to remind myself of this condition and apply it correctly. This is from V to W. H of V is less than or equal to H of W plus 1. So from this node to there, this H, let's call it a P, H of P is less than or equal to this one plus 1. Okay? So, yes?
I know H of S started as N, but how do I know I haven't relabeled it in the meantime?
The algorithm never relabels it, the source.
Sorry, what was the question?
Oh, the question was, how do we know that H of S is equal to N? It starts there. The label on H starts at N, but how do we know it's always N? And the algorithm never relabels. The algorithm never relabels the source, which you know from two ways. Either because last time when I wrote up the entire algorithm, I said V not equal to S, okay, or I meant to. But at any rate, even if I didn't write that up, you only relabel when you can't push, okay? Yeah, okay, let's say that's important. I mean, what does it mean not to be able to push out of S? S has infinite supply. Well, anyway, this is part of the algorithm. Okay? All right. I hope I said that last time, but okay. So this is label N, and therefore this is label N plus 1 at most. Okay? And therefore this is N plus 2 at most. And so what can this be at most? It turns out 2n minus 1. I mean, if you think of, there's a total of n nodes, and therefore there's n minus, at most, n minus 1 of these steps in here till you get to V. And at each point, you can at most increase the label by 1, and so you have that consequence. All right? So that's it. That's the claim here. All right? The labels on any individual node can never get larger than 2n minus 1. And as a corollary, the number of relabels is bounded by, well, I'll just say order n squared. There are n nodes, and the label, when you relabel, you're always increasing a label. Each label is bounded by at most 2n minus 1, and there are n nodes, so the number of relabels is bounded by that, n squared. Okay? So that's a good thing. And notice we've never said anywhere that the capacities are integral. This is not part of the argument at all. So this algorithm, we're going to be able to prove termination and timing, whether the capacities are integral or irrational even. Okay. All right, so what else does the algorithm do? It does relabels, and it doesn't do a huge number of them. It does pushes, okay? All right, now to do the analysis for pushes, it's useful to divide that into two cases. One is called the saturating push, and the other one is non-saturating. So a saturating push is one where you actually use up all of the capacity in that edge. Okay, so definition saturating push from V to W uses all the residual capacity in VW. This might be a forward edge or a backward edge. If it's a forward edge, it means it's pushing an amount in there, increasing the amount of flow up to its capacity. If it's a back edge, then it's going to be decreasing its flow there to 0. Okay. Either case, what a saturating push really means is that this edge VW leaves the residual graph. So VW, it could come back later. After the push. Okay? So a saturating push, if you're looking at a movie of this algorithm and you see that there's a push from V to W, what you'll see immediately after is that that edge VW disappears from the residual graph. Non-saturating is obviously one that doesn't do that. So non-saturating pushes a certain amount from V to W, but that edge in the residual graph VW is still there. Therefore, but there's one thing you can conclude about a non-saturating push. If your non-saturating push is from V to W, what interesting thing happens? Well, when you did a push from V to W, it's because there was excess at V. And if it's non-saturating push, remember what was the amount that you push? It's either the excess at V or the amount that is permitted along the VW edge. So if the amount you pushed out of VW didn't fully use up its capacity there, what it must have done is used up the excess at V. Okay. So a non-saturating push from V to W reduces the excess at V to 0. So that looks like a good thing too. It looks like we're going to be able to use that kind of observation to bound how many times we have non-saturating pushes. Okay, so saturating pushes, let's do that analysis. How many saturating pushes can we have? Okay. The number of saturating pushes is bounded by Nm. So N is the number of, no, that's not right. Nm or Nm squared. We'll do the analysis here. There may be a square in there. Okay. But we'll see in a minute when we actually do it. Okay, number of saturating pushes. I think that's actually right, Nm. All right. We'll see in a minute. M is the number of edges. This is the number of edges. And N is the number of nodes. Okay? So that's a claim. What's the proof? Okay, just let me note one thing. H, okay, so this is consider a saturating push from V to W. Okay? What do we know about H at that moment? H of V certainly has to be greater than H of W. Okay. Why? That was one of the conditions to be able to push from V to W. H of V is greater than H of W. Okay. And of course, VW is in the residual graph at that moment when you're doing it. Therefore, what else do we know about the relationship between H of V and H of W? Well, we proved compatibility. So this was the only condition in the original algorithm, but now that we know that the algorithm, that the preflow and the H are always compatible, we also know this, okay? And those two together say that when they're doing a push from V to W, we have that actual relation, okay? I'm not sure we're going to need that, but I wrote it down here at that moment. So that sort of maybe simplifies things, at any rate. Now, we're trying to count the number of saturating pushes. We're doing a saturating push from V to W, and at that moment we have that relation. Okay, so here you push from V to W. Okay, it's saturating, so that edge goes away from the residual graph. I'm going to try to bound how many saturating pushes you can have from V to W along that specific edge. So we're focusing on a specific edge, and we're going to ask how many saturating pushes can you have from V to W. So when you do a saturating push, that edge disappears from the residual graph. You can't do another saturating push along that edge until the edge comes back into the residual graph. Okay? So you can't. So after a saturating push from V to W, you can't do another, saturating or otherwise, another push from V to W until when? How can you ever do another saturating push from V to W? Well, this has to come back into the residual graph. How can it come back in the residual graph? You have to push from W to V until after a push from W to V. But you can't push from W to V until H of W is bigger than H of V. Okay? But right now, H of W is, in fact, less than H of V. Until H of W increases to more than H of V. In fact, H of W has got to increase by at least 2, right? Well, in fact, exactly 2 if you think about it. So there has to be 2 relabelings of W before you can even do that push from H to W. So H of W, well, I already said that, has to increase. Okay? And I claim, well, I can say it, but H of W is always less than or equal to 2n minus 1, right? Because H of anything is less than 2n minus 1. So at most, I'll just be generous here, 2n minus 1 saturating pushes from V to W. V to W. Okay, so at most, order nm saturating pushes. Okay? So the total number of saturating pushes you can have from V to W, we're focusing on a single edge, VW, and saying, how many saturating pushes can you have? So if you have a saturating push, this goes away. Can't have another saturating push there until it comes back. It can't come back until H of W increases. H of W can only increase 2n minus 1 times. That's actually generous because it has to increase by 2 at least before this comes back. H of W, well, it's bounded by 2n minus 1. So really, you can only have n minus 1. So you can only have n minus 1 saturating pushes from V to W. And this argument was focused on a single edge. There are m edges, So you can only have at most n times m saturating pushes. Okay? So we're making good progress. We've bounded the number of relabels by n squared. We've bounded the number of saturating pushes by nm. Okay? Ultimately, we'll need a data structure to grab hold of a node that has excess. But those are, if you're talking about polynomial time, those data structures are quite simple. We'll see that we want something a little fancier for the most efficiency. But certainly in terms of whether this is going to stop in polynomial time, we're making good progress. And what we still need to do is analyze the case of non-saturating pushes. Okay?